Section 8.1, we started computing volumes of solids. And the basic idea is that we had a solid with known cross sections. So for example, if we have a cylinder, and if we slice it vertically, we have cross sections that are smaller cylinders. If we take this hemisphere, and if we slice it horizontally, we get cross sections that again are basically cylinders. If we slice the pyramid like this horizontally, we get cross sections that are boxes, so to speak. And we use the fact that for a box, the volume is length times width times height, and for a cylinder, the volume is pi times the radius squared times the height. And usually one of these things, LWH, or R or H, usually one of these is represented by a small change in x, such as delta x, or a small change in y, delta y. And what we did is we computed the volume of a smaller part, we added these volumes together to get a Riemann sum, which became a definite integral. Now something that's important to point out is that when we are slicing horizontally, we integrate with respect to y, and when we slice vertically, we integrate with respect to x. So in section 8.2, we're going to be continuing this idea of computing volumes, but the volumes are obtained in a different way. They're obtained by taking a region in the xy plane and revolving it somehow around an axis or a line. So we're going to start by looking at a fairly simple example, y equals the sine of x, the region bounded by the sine of x, 0, pi, and the x-axis, and we're going to revolve this around the x-axis. So to give you a sense of what the solid looks like, it looks like kind of a silly football or an onion or something like that. There's another view. And from the way these drawings appear, if we were to slice these vertically, we would actually get small cylinders, whereas if we sliced horizontally, we'd get shapes whose volumes are pretty hard to compute. So let's go back to the shaded region. We're going to slice this vertically, which means we're going to fix a value of x between 0 and pi, and we're going to pull out a small cylinder of width delta x. Again, because we're slicing vertically, we integrate with respect to x. Now, if I pull that small cylinder out, and remember this is being rotated about the x-axis, and lay it down flat, or on its side, I get a cylinder that looks like this. The height of this cylinder is a small change in x, delta x, and the radius of the cylinder, which I've denoted right here, is the vertical distance from here up to a point on the curve. Well, here y is equal to 0, and here y is equal to x, whatever x might be. So the radius would be the sine of x. If I compute the volume of this small cylinder, I get pi times the radius squared times delta x. So that's a volume of one of these little sections rotated around the x-axis. If I add them all together, I get a Riemann sum, pi sine squared of x delta x. And I'm not going to put any sort of summation sign, indices here. I'm just going to use the summation sign instead, which stands for add up all the little cylinder volumes. As delta x becomes closer and closer to 0, we get a definite integral. The delta x becomes dx, and the summation sign becomes an integral sign where we integrate from 0 up to pi, because the smallest value of x was 0 and the largest value is pi. The value of this integral is actually pi squared over 2, which can be computed using an integral table. In this section, we're going to be less concerned with actually computing the volume as we are with actually setting up the integral correctly. Let's take a look at another example. This is the region bounded by the parabola, y equals x squared, the x-axis, and x equals 1, and we're going to rotate this about the x-axis. If we do so, we get a solid that looks like this. Looking from a slightly different perspective, we get something that looks like a horn. It doesn't look like it's filled in here, but it should be. It's a solid. So it kind of looks like a horn or maybe a Hershey Kiss on its side. Now, again, if we slice this vertically, we can see that we get cylinders. So let's go back to our region, and because we're slicing vertically, integration is done with respect to x, and let's think about a small cylinder that's being cut out. Again, we're taking this section and we're rotating it about the x-axis to get a cylinder. The height of the cylinder is delta x, and the radius of the cylinder would be the distance from the x-axis up to the curve. In other words, from y equals 0 up to y equals x squared. So the radius is simply x squared. The volume of the little cylinder would be pi times the radius squared times delta x, and that simplifies to be pi x to the fourth delta x. The total volume would simply be the sum of all these little cylinder volumes, and as delta x goes to 0, this becomes the definite integral of pi x to the fourth dx, where x varies from 0 up to 1, our smallest and largest values of x. This is an easy integral to evaluate using the fundamental theorem of calculus. I'll let you do it on your own. It's actually pi over 5. Now, a variant on this problem. Instead of taking that region and revolving it about the x-axis, take this region and revolve it around the y-axis. So again, we're looking at the curve y equals x squared, the parabola, but instead of taking this region and revolving it around the x-axis, we're taking this region and we're revolving it around the y-axis. And that's going to have a shape that looks something like this. It's what we call a paraboloid, or kind of a bowl. Now in this case, if we sliced vertically, we would not get rectangular slabs, nor would we get cylinders. So we want to slice horizontally instead. And because we're slicing horizontally, that means we're going to be integrating with respect to y. Let's take a small section of height delta y and pull it out and lay it down. So think about this as being a little section that we're rotating around the y-axis to get a little cylinder. The height is delta y, and we're going to fix an arbitrary value of y, a generic value of y, between 0 and up here, which is 1, because when x is 1, the output is equal to 1. If we lay that cylinder down flat, its height is delta y. Its radius is now going to be a horizontal distance. It's going to be a distance from here over to here. This point has coordinates 0y. This point over here has coordinates xy. But we want everything to be in terms of y for purposes of integration. The change in x values is this x value minus 0. But in terms of y, if we take x squared and solve it for y, we get x is the square root of y. So whatever y is, the horizontal distance is going to be the square root of y minus 0. Let's think about that. If y is 1, the square root of y would be square root of 1, which is 1. We'd have a cylinder of radius 1. If y is 0, the square root of 0 is 0. We'd have a cylinder of 0 radius. So in this case, what we had to do is we had to solve y equals x squared for the square root of y. I'm sorry, solve it for x. So x is the square root of y. Our cylinder then is going to have a volume of pi times the radius squared, square root of y squared, times the height, which is delta y. This simplifies to be pi y delta y. The total volume is what we get when we add together all of these little cylinders, and this becomes a definite integral. The delta y becomes a dy, and the endpoints go from y equals 0 to y equals 1. This integral can be evaluated pretty easily using the fundamental theorem. It works out to be pi over 2. Probably the hardest step in the process for something like this, when we're revolving around the y-axis, is getting the radius down. So here, the x value was 0, and here the x value was dependent upon y. And how we got that x value is we took the graph y equals x squared and we solved that for x, which gave us the square root of y. Now, here's some problems for you to think about. Take a function, a power function, y equals x to the n. Try it for n equals 3, n equals 4, n equals 5, and rotate the region bounded by the x-axis, x equals 2, and the curve rotated around the x-axis and determine the corresponding volume. If x is 2, and if, let's say, n is 3, this y value would be 2 to the third, which is 8. So take a region like this and revolve it around the x-axis. Try it using powers of n equals 3, n equals 4, n equals 5. And then do the same thing. Take a region like this, the same curve, and rotate it around the y-axis. When you rotate around the x-axis, you will have a variable of integration, which is x. So x will vary from 0 to 2. When you integrate around the y-axis, you'll be slicing horizontally. Your variable of integration will be y. Now, if you have a root, like the square root or the cube root or something like that, do the same thing. Take the region bounded by the nth root, let's say n is 2, 3, or 4, the region bounded by the curve, the x-axis, and x equals 1, rotate that about the x-axis to find the volume. Similarly, take this volume, this area, and rotate it about the y-axis. Okay, so try those problems for our next class. See you then.